my statistics students. So anyway, today we're just going to continue with the transformations, the packet we got on Friday. This packet will be your good friend for the next couple of days. We're going to work on the first transformation graph activity today in class as a group activity. Early progress reports are due on Friday. So basically, you all got your latest score when you on the back page of your test number 1. It's probably changed slightly because we've had one more quiz or whatever. So I'll be doing those grades. If you have a grade of like 70 or below, I will probably fill one of these out because 70 is borderline D. So if you're in that range, just know that you will have one of these reports sent to you and your advisor. Project 3 is due on Friday. The review for exam 2 will be on Friday, and your next exam will be on Monday. Any questions about sort of what the schedule is for the next week or so, or expectations? Also, just as a little early reminder, on November 6th is a Tuesday. It's advising day. Okay, so start to think about, if you don't know who your advisor is, find out. And if you have trouble with that, see me and I'll help you find out who your advisor is. And remember the old saying, Joe just reminded me, what was that Woody Allen saying? Life's a lot easier if you just show up. And advising is a lot easier if you show up early. It's a lot easier for you because, as the old saying goes, the early bird gets the worm. And you have like the pick of a lot more classes if you register early. Doesn't mean you have to pay any earlier. So make sure you find out who your advisor is if you don't know, and see your advisor. It's always great to come prepared with the courses you hope to take, okay? And then that helps out your advisor. And then you can focus on other things like your goals, or maybe if you're getting ready to transfer, which maybe some of you are, what courses you have to do to complete your degree and that sort of thing, okay? So that's coming up in, is that next week or the week after? The week after, right? So 2 more weeks you'll have advising day. Okay, so let's continue with the transformations. If you did not complete your survey on Friday, please just drop it in the box on your way out. The left-hand side of the box says Math 107, just throw it in there. And on Wednesday or Friday, I'll discuss with you any changes I can make based on that. Otherwise, I'll just take your feedback and do the best I can with it. Okay, so we had this cheat sheet to fill out the other day. Why don't we just quickly review what we've put in here based on the first part of our transformation work. So if we have a function, it can be any generic function, and we add some number to it, k. If k is positive, what can we say about the graph of the function? Someone want to help us with that one? Yep, the output value shifts up, f of x shifts up by k value, k units, right? You could say the graph of f of x shifts vertically up, or up, I guess, is the same as vertically, k units. Yep, lots of ways to say it. What if we have f of x minus a constant? What would we have in that case? Someone other than Joe? It shifts down. So the graph of f of x shifts down k units. Okay. Okay, so that was the first part of lecture 19, and then we moved on to affecting the input. This first one says the output is affected. F of x is affected. A, F, F, E, C, T, E, D. A for action, right? There's an action taken on the output. That's how you can remember affect versus effect, okay? A is for action. So f of x, the output is affected. When we look at f of x plus k, that's an input change. So the input is being affected. And so you say to yourself, that means there's going to be some kind of change along my horizontal axis versus my output, which is my vertical axis. So this one we talked about being counterintuitive, right? When k is a positive number, what happens here to the graph of f of x? Right, it shifts horizontally to the left. K units, okay? And so I'm actually going to come back up here and say the graph of f of x shifts vertically up. I want to put in the vertical in each of these, in the horizontal. I think it's important just in terms of output is vertical, input is horizontally. So it shifts to the left k units. And now when k is a negative number, so it might look like f of x minus 2, what happens in that particular case? Someone from table 4 over here, what happens to the graph of f of x? It shifts horizontally to the right, right? That's right. We're learning. Right, so that was, again, a little counterintuitive, but really the only things you're going to have to deal with that are counterintuitive in this whole transformation part is when you're affecting the input. The output acts just like you expect, and so you'll see that today when we start looking at a constant times the output f of x versus affecting the input by multiplying it by a constant. So it's really only when we're looking at horizontal shifts or horizontal shape changes that it's counterintuitive. Okay, the last one down here that you worked on in that lecture, some of you completed this before class ended and some of you worked on it over the weekend, has to do with when you take the output and you change every single output of your function to its opposite, what happens to the graph? Mike, what happens to the graph? You didn't? Okay. Someone who completed that? Which axis? We have two of them. The x-axis, okay. So we say that mathematically as we reflect the graph across or about the x-axis, any language like that. And sort of the vernacular that you used that when I was walking around class on Fridays, what did most of you say? You didn't use the word reflect. What did you say? You flipped it, right? Flip f of x across x-axis. That's okay for me, if it makes sense to you. So if we just take all our outputs, envision any graph that you have in your head and think about changing all your outputs, your y values to their opposite, it literally just flips it right across the x-axis. This bottom one says, I'm going to take all my x values and change them to their opposite. And then I'm going to act on it. I'm going to say whatever the function does. So what happens in this case? It reflects about the y-axis, right? Or flipped f of x across y-axis. Now, if you're wondering how you remember this sort of thing, like this particular one here, f of negative x, just think about a straight line like y equals x. Or excuse me, f of x equals x, the identity function. If you switch all your x values to their opposite and they come out looking exactly the same, then your line now looks like, instead of a line with a slope of +1 going through the origin, you now are a slope of -1 going through the origin. You just have flipped across the y-axis. So what's important now for you is as you start working through these different cases, is you should build a little like library for yourself with just a couple of functions that are your favorite and apply some of these things to them in a way that you understand it. And that's really pretty much what your project's going to do for you. Okay, now I just want to remind you, if you somehow are doing good time management or you're not being bombarded with your other classes and you want to get the project 3 into me Thursday morning and put it under my door, Thursday morning, not afternoon, I will have it back to you by Friday so that you could use it to study for your test. Okay? So if there's anything, any issues you're having or any misconceptions, I can straighten them out for you. All right? Otherwise, if you hand it in Friday, I can get it back to you for your test. So if you come in early, you can look it over. But I can't get it back to you Friday afternoon. Okay? So if you happen to, if you've been working along with it steadily as I've been trying to encourage you to do, and you can have it done Thursday morning, I'll get it to you for Friday. Okay? All right, so let's take a look at some of this. So we're going to continue to fill this out. You're going to continue to fill this out as you work through the transformations today. So here's our buddy now. We're very familiar, hopefully, with f of x here. We know from -4 to 2, all the output is going to be 2, 2, 2, 2, 2, 2, 2 on that part of the domain. -4 to 0, we're 2. And then from 0 to 4, where we follow the straight line recipe of -1 times x plus 2. So that's the rule from 0 to 4, and from -4 to 0, we're just the constant 2. Okay, so this says double all your output. Okay, so we already know, before I even double it, what's the output from -4 to 0 going to be? What's the value of f of x going to be? 2. So I can put a 2 right there. F of -4, f of -3, f of -2, f of -3, it's 2. All right, got that down. All right. And what am I going to do to that 2? I'm going to double it, right? Multiply it by 2. So that means for the part of the domain from -4 to 0, all my output is going to be twice as high as it originally was. So I'm going to be up at 4. Okay? So notice the distance now to the x-axis compared to what it was in your original function has increased by a factor of what? 2. Right. Now remember, your language, factor, means you're multiplying. So notice your height above the x-axis, you've increased the distance from the x-axis by a factor of 2. This is very important. Before we were talking about increasing by k units, 2 units. If this is all I gave you, this part of the graph, you wouldn't really know right now if you were f of x plus 2 or 2 times f of x, right? Because adding 2 is the same as doubling, okay? So you've got to be careful what language you use. So here we're increasing this by a factor of 2. That means you multiply every output by 2. That, on this interval, again, you don't know, but when you hit the straight line, then you'll start to see where the difference comes in. Okay, so let's take a look at what was f of 1. We want to double f of 1. Double f of 1. Well, let's see. What was f of 1? F of 1 on my original function took me to 1, and now I want to double that. So I want to double 1. So what do I become? 2. Okay, so now I'm going to be 2. So when x is 1, y is now going to be 2. So here I go right there. Okay. Now what about 2 times f of 2? What's that going to equal? Well, f of 2 was originally defined to be 0. What happens when I double 0? I still stay to be 0, right? So that doesn't change. 2 times 0 is 2. So now my point is 2, my original x, and my new x, which is still 0. So there I go. All right, now I've got 2 more points to find out. 2 times f of 3. 2 times 0 equals 0. Thank you. All right, 2 times f of 3. Well, what was f of 3 on my original function? It was defined to be -1. So now I'm going to double -1, and I get -2. So my new point on my graph is when x is 3, y is -2 now. Okay, and then my final point will be 2 times f of 4. F of 4 was defined to be -2. I double that. and I get -4. So now my new point is when I put 4 into my function, it comes out being -4. So you see, your vertical distance is twice what it was as well. So this is where you get to see the little bit of difference there that exists between adding 2 and multiplying by 2, because you couldn't tell on the constant, okay, when it was constant. That's supposed to be a straight line through those points. But now you see all the distance has doubled for every point. If you look at the distance from here to the x-axis, it's 4 units, when originally, if I take this line right here, it was 2 units. So every point has been pulled down or pulled up. It's been stretched. It's like Play-Doh, that Gumby stuff we used to, well, I used to silly putty, right? It's like, if you look at this black function, which is f of x, and now you look at this new function, let me put it all in green, it has changed shape. It has changed shape. Notice, whoops, notice the domain and range. The domain has stayed exactly the same. The domain is still -4 to 4. But when you stretch it vertically like this, it's got to change your output, your range. So the domain has changed from -4 to 4. What was the original range on the f of x? It went from -2 to 2, right? So if we double it, we stretch it, what should be our new domain? -4 to 4, right? It makes sense. Okay. So we say that we have stretched the graph of f of x by a factor of 2. Okay, that's how we talk about this transformation. We have stretched it graphically, vertically by a factor of 2. Okay. So the graph of 2 times f of x is a vertical stretch of the graph f of x by a factor, this is the critical language, factor of 2. And what that says is that all of your new points, all of the new points on your green function have their distance is 2 times further away from your x-axis because they've all been stretched.
Could you say every point has been either increased or decreased by a factor of 2?
No, it's not going to ever be decreased when you're multiplying by a whole, k here is a whole number. Okay, so it will never. No, we're looking at the distance from the x-axis. So that distance will always increase by a factor of 2. Good question, Michael. Okay. Okay. Any other questions in terms of trying to understand what's happening here? Okay. Yep. The distance from 0. Well, the only way it's related to absolute values that we are looking at the distance from the x-axis, right? Yeah. Anything else before we move along? Let's sing a song. Okay. Now, before you practice this next one, well, actually, I wrote you the general conclusion here. How is the graph of k times f of x when k is a whole number bigger than 1 related to the graph of f of x? Okay, its stretch is vertically stretched by a factor of k. You don't use the word units now because units imply adding and subtracting. We're now multiplying. So it's stretched by a factor of k. The word factor takes care of the multiplication. Okay? Now, I just heard someone say it was vertically challenged. That's a great way of looking at, I'm going to wait and have you practice this one in a minute. Let's go to our next one. Let's go to f. We're still dealing with f of x. But now we're going to vertically challenge f of x. I like that, okay? Because what are we going to do to all of our outputs now? We're going to take half of them. So what's going to happen to the distance? Our new points, if we think about the new points on our transform function, how will their distance from the x-axis compared to the distance each point, the same point is now from the x-axis? It's going to shrink, right? So we're vertically challenged, right? So this is an example of being vertically challenged, right? I like that. I'll use that. Okay. We're going to shrink, baby. Okay. Because now we know what all of our outputs are from -4 to 0. We're 4. But now, excuse me, we're 2. But now we're going to take half of 2 all the way across. So we're now sitting at half the distance above the x-axis. We're now only 1 unit above the x-axis compared to what were we just a few minutes ago? 2 units above the x-axis, right? Okay. So now all you have to do is take every single point. You don't even have to bother filling out this table. Look at your graph and see where you were, and you know how you're being transformed. You're half the person you used to be, okay? All right. Versus your ego being stretched in the first one. So let's take a look right here at 1, and let's forget about this table for a minute and see if we can just do it graphically. Well, on our original function, we were at 1, 1. Remember, we're only affecting the output. The input's staying exactly the same. My output has decreased by a factor of 1/2. So where will I be now vertically? At 1 what? 1 point at 1 comma 0.5 or 1 comma a half, right? So instead of being 1 unit above the x-axis, I'm only a half a unit. What about at 2, 0? Notice black is my original value. Green is my new value. My x value doesn't change, only my output. What's half of 2? Half of 0? 0. So that does not, your x-axis, x-intercepts won't change at all with these vertical shape changes. Okay. Now let's take a look at 3. Now I said that, and maybe you wrote it down or didn't write it down, but that was an important kind of statement, but you'll figure it out. What's, this is 3, -1, right? Now remember, my distance from the x-axis is a unit, 1 unit, or right? 1 unit right here. I'm going to take half of this. So where will I be? At what point? -0.5 or -1/2. So that looks like right there. If I change my color, right in the middle. And then finally, my last point was 4, -2. And right beside each of these points, I'm going to put the new transform point so you can see it as if you had your graph hanging out there right beside it. The table, I mean. Becomes 2, 0, becomes 3, -1/2. So what does 4, -2 become? Kim, can you help me with that? Instead of being -2, instead of being 2 units from the x-axis, what will I be now? 1, right, because it's half the distance. So now at 1. There we go. So now I'm at 4, -1. And now you complete that graph. Okay. And that's what the new graph looks like. So again, the domain has not been affected at all. The domain is exactly the same. It goes from, stretches from -4 to +4. But now, what about the range? It was -2 to 2. Now, where is its lowest point? -1 to 1. So the domain has been affected. Excuse me, the range has been affected. It goes from -1 to 1. Okay, it's cut in half. So we say that this is the vertically challenged graph, and if you wanted to write in general what has happened to this graph, you would say that it has been shrunk or compressed vertically. Those terms are used interchangeably. Okay, so in general, if you have a fraction multiplying your output, a fraction, okay, then we say the graph has been compressed or shrunk by a factor of what? Okay, so notice how this is written. It's k times f of x. Okay, by a factor of k. All right, where it says k is a fraction. Okay, where k is a fraction by a factor of k. Okay. If I had written this like this, in fact, this is, I don't like this. I want to change this. Let's do this. No, I see. Based on that, sorry, we'll keep it like it is. I never had this definition in here before. Where k is a fraction. If k is a fraction, it's been compressed or shrunk by k. I used to have 1 over k times f of x, and then I didn't have, if I put 1 over k now and I have this definition, I have 1 over k here, then it would flip and turn into a whole number, so we don't want to do that. Okay. So you could also, if you want, say it's vertically challenged. I like that, by a factor of k. Kind of like that. That will be like fall 12 107 jargon, vertically challenged by a factor of k. Okay. Just no units is attached to this. Okay, so you have 2 practice problems to work on in the packet. So if you move back a page, work on those 2 practice problems, and then we'll move along to the horizontal. So now, folks, you're changing the shape. Friday, all we did was pick our graph up and move it up and down the y-axis or right and left. Now we're stretching it or shrinking it. So we're changing the shape of the function. Today we're changing. So let's go to this graph here, which is a k of x here. What is k of x here? What is this original function, k of x? That's the absolute value. So we know something about the output of this function. All the outputs are 0 or positive, right? So we call that non-negative. Everything is above the x-axis. So we know k of x here for each one of these values is going to be 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. That's k of x for each one of those values. They come out without their sign, right? If it's negative, it comes out being positive. If it's positive, it stays positive. They all are positive. And then what are we doing to every single one of them? We're tripling them. So for the same exact x value, our distance now, instead of being a distance of 4 above the x-axis, as it originally was, you're now up to 12. Right? So now your distance has increased. The distance is 3 times what it was. It's increased by a factor of 3. So at -3, you were +3. Now you're going to be +9. So once you get the hang of this, you don't have to fill out the table. You can look right at your graph. At 2, you were 2. Now you're going to be 6. At 1, you were 1. Now you're going to be 3 times off the x-axis. 0, 0 stays the same. And we know that our graph is symmetric. So once we have one half of our graph, we have the other half. So we now look at this. We connect the dots. What did I do? Oh, 3, 6. Oops. Yeah, I threw these off. Okay. 9 and then 12. Okay. So if we're comparing, remember, our transformation is, what are we transforming from? We're transforming from this original function here, the black outline function, which was your absolute value function. We call that k of x. So what's happened to k of x? The graph. So when we start to write what's happening, we always want to talk about it in terms of our original graph. The graph of k of x has been stretched up. Some people say it's more skinny or narrower. That's how some people see vertical stretches. The graph of k of x has been stretched. by a factor of 3. Now, I'm going to say this, and I'm going to say it once, and if it like floats over your head right now and you don't want to take it in, you know, like I have a friend whose son goes like this when he doesn't want to hear something, and he's 42 years old still, but he still goes all right? So if this is one of those things, just go like this, all right? So one of your fellow students just said to me, isn't this taking this thing and like putting a vice here and compressing it this way? Couldn't I talk about this as being a shrink or a compression? Well, there are some functions that you can look at them and you can say that this is vertically stretched by 3 or compressed by a factor of a third. Because they're the same. In other words, take a look at 3, 3. So put your eye at 3, 3. Here we are, 3, 3. If we're talking about vertical stuff, we keep our position anchored at 3 and we go up to the output to see what's happened. So this output is 3 times taller, 3 times further away from the x-axis. If we talk about horizontal compressions, which we haven't done yet, we haven't done it, then you're talking about now keeping your anchor at the y value and seeing how far from the y-axis you are. So let's see, how far are we from the y-axis on this original function? We're 3 units, right? How far are we if we keep the same y value when we're at this point? 1. So our distance from the y-axis is a third of what it originally was. So Nils asked this question. I don't usually talk about this till Wednesday, but there are some functions that you could make claims are actually either horizontal compressions or vertical stretches, depending on how you see it. It's kind of like those optical illusion things that people, right, is it the old woman or the rabbit? You know, you've seen some of these optical illusion things, right? So when you get a little more versed with the horizontal compressions, we can talk about this. But there are some functions like your greatest integer function you just worked at. The reason we put that in is when it's a vertical compression or stretch, that's what it is. But some functions, just think of a straight line for a minute. Think of what f of x equals x, your identity function. Now do f of x equals 2x. You can either say that at each x value it's twice as far, or for the same y value it's half as close. So you can kind of play the game of, is this really a vertical stretch or a horizontal compression? But, you know, don't let it mess with your mind if you don't want to. You don't need to know both of those things. Okay, and then you worked with the greatest integer function next, which you have to work with on your project. And what did we say we were going to do to all of these values? Yeah, so what happened to them? What happened to this part of my greatest integer function that was right along the x-axis where it stayed the same? So that I can just put over as green. Now, on the interval from 1 but less than 2, I was 1 unit above the x-axis. What did I become now? A quarter, which notice I have the proper scale today on today's notes for that. All right. And then instead of being 2, I'm a quarter of 2, so where am I? Half. So this whole function, okay, this whole function has been compressed, seriously shrunk. Talk about vertically challenged. It has been seriously vertically challenged, okay? And then 3/4, okay, thank you. Looks a little strange over here, okay. Right here, oops. Okay, so this one has been, so here m of x has been vertically compressed or shrunk, however you want to say it, okay? It doesn't matter, compressed or shrunk by a factor of 1/4, okay? By a factor of 1/4. Okay. Okay, again, this is affecting output values. It's intuitive. If you see something being multiplied by a whole number, you expect it to grow. If you see something being multiplied by a fraction, you expect the distances to shrink. Very intuitive. Next, we deal with the horizontal shape changing. Okay? Horizontal shape changing. So here we are back to our friendly f of x. Okay? But I can't just suddenly write down the output values right now because they're changing. X is being multiplied by 2 before I even apply the function to it. So this is the first thing when you start to look at your transformation stuff and you see something like this, you say, uh-oh, input, oh, geez. Okay. So now we're affecting our input. When we affect our input, we expect something to happen along the horizontal axis. So if our shape is changing, it should be changing by either smushing the function together, compressing it, or stretching it horizontally. Okay, so our input's being affected, so our shape change is along the horizontal. So shape change along horizontal axis. Okay, so before you even begin, you can get a sense of, what's being affected. If it's the input, then you know it's always a horizontal effect. Okay, so notice all I did here was put what I have, f of 2 times, and now I'm going to put the x value in as it originally was, -3, -2, -1.5, -1, 0, 1, 1, and, oh, that should be 2. 2 times 1.5, and 2 times 2. Okay. So f of 2 times -3 becomes f of -6. Is that defined? No, not defined. We can't plot that point. Dot, right here, dot, times, yep, okay. And then f of 2 times -2 is f of -4. Is that defined? F of -4 is defined to be what? 2, as it always has been. But what's my x value now? It's -2, 2. So I go to -2 and I go up to 2. So notice, if I pick any input that's less than -2, like -3 or -4, I'm not defined because I'm being doubled before I even get to go into my function. And my function starts at -4. Okay, so now let's take a look at 2 times -1.5 is -3. What's f of -3? 2. And so that means that my new point is -1.5, 2. So I go to -1.5 and I get to go up to 2. And now I have 2 times -1 inside, that's -2, and I know f of -2 is defined, it's 2. So when I'm at -1, I'm 2. So now I'm at -1, I'm 2. So notice all these points are being squished towards the y-axis. At 0, I am still 0. 2 times 0 is 0, so at 0, I am 2. I keep my color format going here. I could have put in -0.5, and if I double it, I would have been -1, and I would have been, excuse me, yeah, I would have been -1. I already did that. Did I do that? Yeah, okay. So there I am. So notice what's happened to my domain. It started at -4. Where does it start now? -2. It's half the distance it was. Instead of being out here and being 4 units away from the y-axis, I'm now only 2 units. So my function is coming in. It's like taking a vise, and it's like taking this vise and applying, you know, those walls in those horror movies that are closing in on people to squish them, right? That's exactly what's happening. The pressure is on, folks, okay? All right, so let's go to 1. Let's see what happens when x is 1. We used to be 1. Now let's see what happens to us. If we double it, we're going to be called 2. And f of 2 was what? 0. So now we're going to be at 1, 0. Okay. Now we're at 1.5. And now we're going to be called f of 3. And when we were 3, we used to be negative. We were defined to be negative 1. So at 1.5, we're going to be negative 1. Now when x is 2, let's see what we are. We are 2 times 2, which is f of 4. And f of 4 was defined to be negative 2. So now we're 2, negative 2. And we're done. That's it. So this whole function gets squished horizontally by a factor of 1/2. So that totally changes the shape. What's happened to my range? Stays the same. Absolutely nothing. I'm still going from negative 2 to 2. So when I look at f of 2x, it goes against our intuition. You think about doubling it, you think, oh, maybe this is stretching it horizontally, but it means your x value has to be, to get back to where you were, it's a little harder to say, to get back to where you were, your x value has to be half the size it was. I mean, I can say that because I've looked at these for years, but if you think about 2, 0, right? Here's 2, 0 on our original function. Now you're 1, 0. That's because the x you put in here, when you double it, becomes your 2. So your x's, to be back at the same y value, your x's only have to be half as big as they were because they're all being doubled. You're doubling all your input. So to be who you originally were, you only have to be half your size because you're being doubled. So we say here that f of 2 of x is the graph of f of x horizontally. That's why it's important to always talk about things horizontally and vertically. Horizontally shrunk, compressed by a factor of 1/2. So even though there's a 2 multiplying the x, so horizontally compressing it by a factor of 1/2 because your distance is half the distance from the y-axis. Okay, so all these points are half the distance from the y-axis. So what do you think is going to happen now if I change this number in front of x to be a fraction? What do you think is going to happen to the graph? Brian goes like this. It's going to be stretched horizontally. Again, exactly what you expect to have happen. So let's take a look at that. You can practice this one at your seats. 4 times x, and I've given you a piecewise, okay? So you should expect, think about what this would look like if you could take the walls and with equal pressure, push this in. Okay, so think of what's going to happen to the shape of that graph, okay? But I want to do this last one with you, f of 1/2 of x. So now your x's are being multiplied by 1/2. So to get you back to where you were in your original function, your x value has to be how many times greater? Twice. Because look, to get to negative 4, I'm defined at f of negative 4. That's my first point. I have to now be negative 8 because you're going to take half of me before I even get to define myself. The first point isn't defined because half of negative 9 is 4.5, negative 4.5, and I'm not defined. So what's f of 1/2 x here? F of 1/2 times negative 8 is f of negative 4. Hey, I'm defined, I'm 2. But what's my x value now? Negative 8, 2. So I got to come all the way out here. And let's do every even one. So half of 6 is going to be, half of negative 6 is going to be f of negative 3. That's 2. Right? Half of negative 4 is negative 2. That's defined. as well. So now you notice all of your x values have to be twice as big. It's being stretched. So now let's try -2. Half of -2 is f of -1. That's still 2. So my point is 2, 2, -2, 2. F of 0, what was it before? 0 was 2. What is it now? Still 2. Okay, so you can see this whole thing has been stretched. It's like taking that original function and pulling it this way by a factor of 2. You can do each of these points now as well. 1, 1 will become F2. 2, 2 will become f of 4, and you're done. You just got 2 more points to plot. So the graph has been horizontally stretched by a factor of 2. It's the reciprocal of the fraction. Okay, so I'll put in these last ones for you. F of 2 is 1/2 times 2 is 1. F of 1 was 1, so it's 2, 1. F of 4 is the same as F of 2, which is 0. So at 4, you got a 0. And then, of course, F of 6 is the same as F of 3, which is -1. And then F of 8 is -2. So this whole thing has been horizontally stretched. Oh, there's no arrow there. It stops right there. So it's like taking that thing and going whoosh. Okay. So remember, input is counterintuitive. It's the opposite of what you expect to have happen. Okay. The output, when it's affecting, is exactly what you expect to happen. Okay. So unfortunately, because of the fire drill, we didn't get to work on that group activity that's right at the end of this lecture 20. So please work on that before you come to class on Wednesday. Okay, see you Wednesday.